All right, thanks for coming along, everyone. Today, Danielle is going to give her talk about multimodal interaction for enhancing team coordination on the battlefield. So, a big hand for Danielle.
Thank you. Okay, so today I'm going to talk about part of my thesis research and then kind of give an overview of a lot of the efforts that are going on in my home lab, the sketch recognition lab back at Texas A&M University. And if you guys have any questions about any of the projects that I'm discussing, feel free to stop me and ask. Okay, so sorry for the lag. A lot smoother last time. Okay, so the domain of my research is the U.S. military. They're currently researching technological tools to support team coordination on the battlefield. And in that area, our focus is on improving team navigation and assembly, and also increasing team and situational awareness. And then a branch of research has taken us into exploring human-drone interaction as well. Okay, so first I'll start by giving you a little background on the main problem that started our research in this area. Our focus group is our paratroopers, and paratroopers are soldiers that are trained to conduct airborne operations. When they conduct their operations, it usually involves the rapid assembly of thousands of soldiers, hundreds of thousands of soldiers, in time-critical situations where they have either little or no light. They have to maintain radio silence, and they're usually dropping into large, unfamiliar territories. And at the same time, these paratroopers are loaded with about 200 pounds of equipment. So fatigue is a big problem as well. Oh, can you guys see that okay? Yeah? Okay. So I don't know if you can see this image here, but each of those little dots is a paratrooper, and they're like, yeah, maybe a little. I can see my screen this one. No? Yeah, that's better. Cool. Okay. All right. So the way they currently do this now is they jump out of the planes. Oh, I have my video. Cool. Well, I'll go ahead and show you this while I'm talking. All right. So the way they conduct their airborne operations now is basically they line up and they jump out of the planes. The unit commander, calls out instructions and basically tells them when they need to line up and get ready to drop. Now, they're not allowed to hesitate for more than a second, really, because 1 second in the sky is actually a long distance on the ground. So if they stand at the door and they hesitate, they're actually pushed out, which is kind of fun to see. And then as they're falling, and you'll kind of see this soldier who's jumping here do the same thing, the way they orient themselves is as they're falling, they have to try and look up and see which way the direction of the plane is going so that they know, which way their rendezvous point is in direction to the flight path. In addition, all of the equipment is pushed out of the plane before they drop. So in order to be able to navigate backwards to follow their equipment, when they hit the ground, they have to look up and see where the plane is going and then go the opposite direction. So it's not a very accurate process. And in addition to using the direction of the plane to orient themselves, they also have these Steiner aids, which are shown, in this image here. And the Steiner aids are infrared chemical lights that are mounted on a 15-foot pole, and you can only see them using night vision goggles. So 2 soldiers are usually tasked with erecting these Steiner aids at the location of their assembly points. Now the problem is the Steiner aids are heavy and they're not easy to wield, so it actually takes 2 guys to hold it up. And usually what happens is some of the soldiers will arrive at the rendezvous point or start looking for the rendezvous point before the soldiers that are carrying the Steiner aid. So, if they're not there, these guys can end up running around lost for quite a long time, even hours. So assembly can take up 20 minutes is the quickest time for the most trained and seasoned group of soldiers. And in most cases, they usually lose a couple of people or, take hours to assemble when the team is inexperienced. Okay, so our objective to address this problem was to create an adaptable system that could be used to increase team coordination and decrease the assembly time. We knew, yeah.
Mm-hmm. Is the assembly point known before they before they land, or is it then just established after they land, or is it already a strategic decision? We want to assemble this point.
Right. It's a strategic based on kind of an aerial map of the area, so they know approximately where they're going to drop, and then based on the four corners of the drop zone, they'll say, okay, on the east side of the drop zone, Unit A is going to assemble. On the west side, Unit B is going to assemble, and so on. And some teams have to assemble at a heavy drop location, which is either a tank or equipment or anything they need to get to.
So why wouldn't they just wear a small GPS?
And rendezvous at a particular location, because it might not, so if for one reason they don't use, they use compasses and maps, and they do use GPS units, but for training purposes, they don't want people to have like units that have built-in like GPS locations already programmed into them, if that makes any sense. In case, like for instance, their equipment gets compromised, they don't want to have actual location, like physical locations that their soldiers are going to be located prior to the drop. Does that make any sense?
Yeah. No, probably just becomes clear.
Okay. Basically, they don't want to drop with having that information ahead of time. They don't want to say, okay, this is where everybody's going to be located, because if somebody gets captured, then somebody else has that information. This is where everyone's going, right here. Okay. Yeah. So we knew our solution had to support mobility. It had to be lightweight. We couldn't emit any light or noise pollution that would draw any unwanted attention. It had to be based on established procedures, and of course it had to be easy to use and possibly have a hands-free component. And the communication component had to be able to span the distance of a drop zone. And of course we wanted it to provide both situational and team awareness and promote team coordination. Okay, so going into this area, we were pretty surprised to find that in the military domain, there weren't very many systems that were already built to kind of address this problem. There were a couple of systems that we did get to test out that had been kind of discontinued. The one that I have a picture of here is called the DZAZ Drop Zone Assembly Area System, and it used radio frequencies. Sorry, can you still hear me? Okay, sorry, I knocked it. It used radio frequencies to kind of orient the soldiers to the location of their equipment, and it was really, really heavy. It actually made my arm hurt. But what they would do is they would turn on this radio receiver, and it would have lights that would get more intense as you were pointing in the direction of the radio signal. So you just kind of had to spin in a circle, like kind of like an antenna, and go the direction that the radio signal was the strongest. So wasn't very intuitive, and it only added to the already unbearable weight that they were already carrying. So not a very good implementation. Okay, so prior to starting development on this application, we actually spent a couple of months at Fort Bragg, North Carolina, to conduct an ethnographic analysis of the paratroopers. And during interviews, we found that, of course, the assembly time is the most confusing and chaotic time of the mission, because, I mean, you have 1,000 guys jumping out of a plane. They kind of hit the ground. They're all mixed up. You don't really know, they don't really know where their units are, and they all have to navigate to some assembly not definite assembly point based on, intelligence that they received prior to jumping. So some of the younger, inexperienced soldiers relied heavily on technological devices, and we actually found out that even though they weren't supposed to, they kind of confessed to us that they use Google Maps during training to keep from getting lost, which of course they're not allowed to do, and they're using technology that won't be available when they actually drop in the field. So when talking to the soldiers, we also found that they were really, really divided on their opinions of how much information was required. Some of the older seasoned soldiers just said, well, I know what I'm doing out there. I don't need any GPS. I don't need any help. And some of the younger guys was like, oh yeah, I want a helmet that tells me like where all my teammates are. And, so everybody wanted something different. The only thing that they were, that pretty much everybody had the same opinion on was what to do if, for instance, they get compromised during a mission. They were supposed to shoot any type of equipment that contained any intelligence, which is why they can't have pre-programmed locations in their equipment when they drop. So we wanted to try to avoid that because we really like our phones. We didn't want them to shoot them. Okay. So now I'm going to talk about the solution that we came up with to address this problem. We developed a location-aware solution using commercial off-the-shelf components. And the way the system worked in a nutshell was it created an ad hoc Wi-Fi network that would broadcast and receive encrypted GPS coordinates when they were obtained during the drop. And it included multiple views for displaying the navigation information. Okay, so the hardware components that we used was a ruggedized computer, that's the Panasonic Toughbook on the left, and we fitted it with a Wi-Fi antenna and a GPS unit. And then for the receivers, we just used Android phones. I believe those were, gosh, I don't remember what those were. I'm sorry, my mind was blanking. We've gone through a bunch of different models. I can't remember what the original one was. Sorry, I'll come back to that. For the user interface, we had one user interface for the beacon operation, and then, like I mentioned before, we had multiple views for the receivers, and then all of the UIs, we created a night mode to reduce the light pollution on those. So here's the beacon interface. The way it would work is they would attach the ruggedized computer to any equipment or tanks that needed to be pushed out of the plane before they jumped. And then they would set a delay for the broadcast, and then set a delay for the broadcast. And then as soon as the equipment was pushed out of the plane and once it hit the ground, then it would broadcast its location once it hit the ground. So its location wouldn't be known before it went out of the plane. And you can see what the live screen would look like. So basically the beacon is showing its location and then also the location of other beacons in the area, which I'm going to explain a little bit later. Okay. And then here's the views that we created for the receiver interface. And it was based on feedback that we got during multiple tests with the paratroopers at Fort Bragg. Basically, that kind of goes in order from least information to most information. This view just shows the distance to the beacon that's selected, and then the next one actually points in the direction of the beacon that's selected. The third one mimics the compass that the soldiers are currently using, and then also points to the location of the beacon selected. And then the last one provides an overview of the military grid reference system that they work in. So they don't use GPS, they use MGRS coordinates. So it shows the grid and then also the location of all of the beacons relative to the phone's location. So they wanted, so for this one, they just wanted to know, which way is the beacon that I'm going to. For this one, it provides the bearing information as well. So yeah, they'll go to that point anyway, but for any reason they say, okay, I need to know which direction I'm going in relation, so that I know where my other teammates should be located in relation to where I'm going. So it's just like, if I know I'm traveling south, then, like this team that's running that way is probably like unit A, or this team going that way is probably unit B because they're going east and they're going west or something like that. So just, they wanted to have that information. It was mostly for the unit leaders to be able to say, if they could communicate with each other when they rendezvous. Okay, good question. All right, so this shows, sorry. Yeah, the light's still on, so I think it's okay, right? So this shows the night views for both the beacon interface and the receiver interfaces, and here shows what it looks like using night vision goggles. So at nighttime, the views without night vision goggles, you wouldn't be able to see this outside of a range of about 3 meters. So it worked fairly well. Okay. So now I'm going to talk about how the communication took place in the system. So the beacons would broadcast an encrypted position over the ad hoc Wi-Fi network, and each beacon antenna had a broadcast range of about 565 meters. So what we did was we encrypted the location of each beacon and embedded it in the SSID, the service set identifier. And we set it up that way to kind of circumvent the problem of people having to actually connect to a Wi-Fi access point. So using this method, we can pretty much deliver the location information over the Wi-Fi network to, an unlimited number of receivers without, hitting that connection cap problem. So the way it would work is we had 32 ASCII characters available in the SSID. We took a 4-point precision of the Latin long because, we knew what hemisphere and continent, hopefully, that we were on, so we didn't need to transmit that information. So we just took the last 4 precision points of the Latin long data and the ID and then the most recent timestamp of the signal. And, oh gosh, let's see if we can put this on a little better. Sorry. Okay, and then we converted it to byte values and then compressed it. And then after we had, if there were 3 beacons within range, then we would append 3 different beacon locations into one SSID, and then we would encrypt it, broadcast it, and then on the other end, decrypt it, and convert it to the Latin long coordinates and the timestamp and the ID. Okay. So the way the broadcasting would work is each broadcast interval lasts only 5 to 10 seconds, which is another reason why the connection wasn't needed. So the beacon would broadcast the signal for 5 to 10 seconds, and the Android phones would then search for a specific SSID with a specific format. And once it found an SSID that met that format, then it would take the SSID and then decode it and get the GPS information and then point to where it needed to go. Now the beacons would produce a daisy chaining effect. So like I mentioned before, it would broadcast its own signal, but also the signal of any beacons that were in range. So with each broadcast, it could broadcast 3 beacons at a time. And then it would continue to do that until all of the beacons in its list had been broadcast and then start over again. Does that make sense? Okay. So during our time at Fort Bragg, we conducted about 4 user studies in the test drop zones. And the purpose of those studies was to evaluate the effectiveness and usability of the system. We had about 50 soldiers of the 82nd Airborne Corps that had varying levels of experience using compasses, maps, GPS, smartphones, computers, and mobile apps. We set up 3 assembly points in the area and asked them to navigate to each of those assembly points using our solution system. So after the study, we found that every participant was able to navigate to all the assembly points in 25 minutes or less. So that's about 8 minutes per beacon, and which is about a 60% reduction from the best assembly time recorded for a team navigating to assembly points during a training exercise. And the feedback that we got from the soldiers on usability and effectiveness was very good. They were very pleased with the solution, and they thought it was really easy to use, and we really didn't have to show them, how to use the system. Mostly the soldiers seemed to be very excited about learning it and picked it up pretty fast. So going into the next phase of the project, we got feedback from the soldiers saying that they wanted to be able to know, since they couldn't talk to their teammates, they wanted to be able to know if for any reason their teammates needed assistance, or if they didn't show up to a rendezvous point, if they needed help. So, at this point, we had a really good understanding of the problem domain, and we had developed a lightweight, cost-effective replacement for the Steiner aid. And I didn't mention before, sorry, the MGRS map was actually not available commercially or in the military domain, so we were able to provide that for them, and then also the ad hoc notification system that did not store GPS information, but just delivered it real time when the equipment or rendezvous points landed. So it kind of mitigated the security problem that I mentioned before about having predefined coordinates. Okay, so going forward, we wanted to, like I mentioned before, be able to increase usability. We knew that soldiers couldn't be running around, staring down at phones the entire time. That wasn't a good way to spend their attention. And so we also wanted to minimize cognitive load on that same front. So in order to do that, we wanted to be able to provide hands-free solutions, and to address that, we explored augmented reality and haptics as possible solutions. So haptic feedback, you guys know what haptics are? Yeah, okay, cool, I'll go into that. So in order to provide haptic feedback, we utilize the vibration feature on the Android phones. And so in our initial implementation of it, the frequency of the vibration increases as you get closer to the beacon, and as you're facing the beacon, the vibration turns on and off when you're facing the beacon, and then the frequency increases as you're getting closer to the target beacon area. So one of my lab mates is currently researching the complexity of messages that can be delivered using haptic feedback as part of his thesis, so it's currently an ongoing effort. And I took this route. So I wanted to be able to provide an AR visualization that is based on a concept that the soldiers were pretty much familiar with. I think every soldier that we interviewed that was younger than 25 was a gamer, avid gamer for that matter. So when we kind of presented them with, the concept of a head-mounted display and the different UI elements, of course, people were talking about Halo and Ghost Recon and, like all these games that they were really, really familiar with. And, it's become even a kind of a recruiting tactic. The military has started creating these training simulations that are modeled after really popular games to, get these new recruits excited about their training and kind of capitalize on things they're already interested in. So we wanted to do the same thing. So our first prototype was using the Wikitude API, which was kind of a pain, but it was decent enough for us to be able to see if this was a viable way to take the implementation. So it basically just launched a separate Android activity, and then we passed the GPS data from our activity to the Wikitude activity and displayed the location of the beacons using the camera phone. So we conducted a preliminary test to evaluate, whether or not it could be used as a possible visualization medium. And we conduct this test with local ROTC cadets that had similar paratrooper experience, so kind of the same domain. And we asked them to use the AR prototype interface to navigate to 3 assembly point beacons. So it was kind of a repeat of the original test that we did at Fort Bragg. So we were glad to find that all of the participants were able to navigate to the beacons in less than 15 minutes. So still had a good assembly time. And the only problems were that the participants using the AR view reported that the tags kind of drifted a little bit as they got closer, and glare was also a problem. So we knew that we really didn't have to adjust the glare since the paratroopers only jump at night, but they were still able to locate the beacons on site. So we decided to pursue development with that. And then that's when I came to the HITLab last year. Yay! So working with Dan, I was able to use the outdoor AR library to create an interface that would work with our solution system. And we integrated it with GeoTrooper and then used it to create points of the beacon locations in the real world view, same as with the Tube API, but with a lot better. And then using a previous application he had developed, I was also able to implement that target view that would, when it was centered over a beacon location, it would pop up information about the beacon and provide more information without the soldier actually having to use his hands to interact with the phone. So what the soldiers did is they would either clip the phones to their weaponry and kind of use it as a viewfinder and get information that way. So it proved to be pretty effective. Okay, so we conducted another user study, and this time the feedback we got was much better, and we didn't have the drifting problem, and the glare wasn't a problem because we conducted this one at night as well. And then we found that the soldiers were able to navigate to all of the points in less than 15 minutes. And the only comment that they had was that, glare was an issue. We did do this one during the daytime. The main issue that they had was the occlusion of the symbols that we used to identify the beacons. As they got closer to the beacons, they wanted them to either disappear or get smaller so they could actually see the location of their rendezvous points that they were navigating to. Okay, so at this point we had developed an AR visualization of our beacon network, and we had kind of capitalized on the way that they're currently navigating to their assembly points. So instead of having to look down at phones, they could kind of look up and scan the horizon for the location of assembly points, the same way they're currently doing with Steiner aids. So it allows greater situational awareness and also promotes hands-free interaction with either the use of a head-mounted display unit or by clipping their phones to their weaponry and using it as a viewfinder. Okay. So moving forward, we wanted to be able to provide an overall, we had kind of the situational awareness thing tackled. We wanted to be able to provide teammate awareness as well. A lot of the soldiers mentioned that they wanted to know when their teammates were in danger. So rather than having them kind of have to interact with their phones by pushing a button or pressing an alert or button on their phone, we wanted to kind of maintain the hands-free interaction. So we looked into the use of physiological signals as alerts instead. So we wanted to be able to use the physiological signals as triggers when a teammate was in danger. And in order to do that, we had to make the phones work as beacons as well. So the way we did that is we had the Android phones establish their own Wi-Fi hotspot with the same encrypted signal process that the beacons were using. And we also gave the phones and the ruggedized computers unique identifiers so that when we visualize them, the soldiers will be able to see specific icons that represent beacons and then other unique icons that would represent their teammates. Okay, so we created this color coding system to allow the soldiers to quickly identify, whether a teammate was in danger or whether a teammate was just tired or maybe possibly engaged. So like a level of severity, red, yellow, and blue. And I stole that from Star Trek. So like red, yellow, blue alerts. Yeah. So we obtained our data using the Zephyr bioharnesses. I think I might have used some of you as guinea pigs last year. I can't remember. But it's a harness that kind of just fits across the chest, and you can get heart rate, temperature, skin conductivity, which is, how much you sweat, respiration, posture, all of that information, and it delivers the data via Bluetooth to an Android phone or any Android device, pretty much. And so we sought out to identify four different states we wanted to identify a state of surprise. So if somebody was surprised by an enemy, we wanted to identify a state of focused attention, which we used with an EEG headset, which I'm going to talk about in a second. And we also wanted to identify a state of physical harm, like if a soldier was hurt and whether a soldier was tired. Okay.
So what's one of these devices you can also know all these.
Say that again?
If one of these devices, for example, was captured by an enemy, you will know all the locations of the other soldiers.
No. So when a soldier gets their procedure is when they get compromised or they're supposed to shoot their phone or destroy.
If the device get into it,
yeah.
This enemy can imitate. There is no way you can verify that this is an enemy or a soldier.
Right, you're right. And we did kind of implement some fail-safe things for that, which we can talk about in a second. It's kind of related to this. But yeah, since they have their own procedure for how they do it, they didn't actually fund us to kind of create security measures for that, but we did anyway. Okay, so yeah, in our pursuit of trying to identify a surprise state, previous research has shown that you can measure a state of surprise by a change in how much a person sweats. But of course, since these guys are running, carrying 200 pounds of equipment, they're sweating already. So that was kind of a bust. It was really difficult to identify changes using that. And then we also wanted to use an EEG headset to identify a state of focused attention, and that was also very, very difficult. The data wasn't consistent among the individual soldiers. So one of our master students is still kind of pursuing to see if we can get those states identified. So it's still ongoing. But during our first round of this effort, we really didn't get anything for surprise or focused attention that we could use. However, a state of physical harm was really, really easy to, well, I want to say really, really easy, but it was easier to kind of classify. Basically, a normal heart rate, resting average is 60 to 100 beats per minute, so anything below 55 should generate an alert. And also the harness would be able to identify if there was a problem with the signal. So if there's no problem with the signal and the heart rate is correct, then and less than 55 beats per minute, then we can assume that the soldier is in danger. Kind of stemming off that, if the heart rate is low and the soldier is not moving, then the phone locks itself. So if after a certain amount of time the device's GPS doesn't change a significant amount, then the phone will lock. So that's kind of like one of the security measures that we implemented. Excuse me. Also, if there is, if the soldier is in a prostrate position, so if he's lying flat on the ground, obviously he's not moving, then it automatically generates an alert regardless of what the heart rate is. Now, of course, for the heart rate being less than 55 beats per minute, we had to simulate it because ethically we could not kill somebody and test that. But I don't know if those change in the future, maybe. But
so what if one's injured? How big is going to be the heart rate? Like if someone gets injured,
yeah,
whatever.
Right.
Yeah, how big is the heart rate going to be then?
So the only two that we implemented using heart rate was if the heart rate is less than 55 beats per minute or more than 100 beats per minute and the soldier is not moving. So like basically your heart is going crazy, but those two things in tandem. I think those, I don't know, we're still trying to come up with more. It's kind of hard to, like these we kind of came up with on our own and then tested them and found that, simulated them and found that it was okay. The ones that we're trying to discover now, we actually have to get, human participants to do stuff and then try to find patterns. Yeah, we just smack them around. Like, how do you feel? How's your heart rate? No, we try to exert them. So every Friday, the ROTC have to go through their physical training, but on Fridays it's more intense than like the other day. So we'll usually like strap them on or strap on a harness and just kind of follow them around and usually the team leaders are really, really nice to us. They'll single out a couple of the people that are wearing harnesses and make them do more stuff so we can get more data that we can use. So technically we're not torturing them, their team leaders are. But hopefully we can come up with more events based on that. Yes?
You attach the heart rate monitor to them, like say if they're doing martial arts training, so get hurt. And that way it's not like during a boxing match.
Yeah, I don't think they actually do any like hand-to-hand combat training in our. That's a good idea. Yeah.
Get beat up, or they're going to get beat up anyway, and then just monitor or they're getting beat up.
Yeah, no, that's a really good idea. I might. Yeah.
I'd like to say, paintball, like imagine you shot with a paintball.
Yeah. Yeah. My only concern would be like the equipment. I don't care about them, but like if the equipment gets hit or something, that'd be a problem. But that is a good idea. But I think boxing might be better. Are you allowed to hit here?
Yeah. But I'm sure you could strap it to their back or have the band or the sense bit at the back.
Oh well, no, it has to be like right here on his arm. But
you just say don't punch them there.
Don't. Okay, good suggestion.
Like other heart rate monitors or other.
Yeah.
Strapped to people's backs.
Yeah, we could definitely like look at other types of sensors. That's a good idea. Thank you. Okay, so here's some of the the tests that we conducted with people to try to find a measure of fatigue, which was a little bit harder than coming up with triggers to identify physical harm. So what we did is we kind of based this on previous studies and had some of the soldiers exert themselves to a point of exhaustion. And we found that if there's less than a 15% recovery rate in your heart rate, then that can be used as a measure of fatigue over time. So the top graph just shows a person's heart rate as they're currently doing like interval training. And then the bottom one just shows the steady decline in like heart rate recovery over time. Okay. So we conducted a field test to kind of evaluate the communication and then also the physiological triggers. And we basically had one person kind of pretend to be the injured teammate. And we had him exert himself and then also lay prostrate and basically test all of the triggers that we had implemented. And then as the events were triggered, it would broadcast an alert signal throughout the system, and then all of their teammates were able to then focus on that injured soldier's location and then go find him. And without using any type of signal amplifiers or any of the beacon amplifiers, it got a broadcast range of about 100 meters, so that was just between the phones. So it was pretty good. Okay, and then we conducted a formal user study using both beacons and the receivers as broadcasters. And we kind of set it up like a game, so we divided people into two teams, and then we made one person be the injured party, and we did this all at night. So the injured party would go out and he would die or get hurt, so to speak. And his harness would then send the information to his phone, which would then interpret it and send the message throughout the ad hoc network. And then the teammates would then navigate to his location and rescue him and then continue on with locating the beacons, which was part of their mission. Okay, so using that approach, we saw that all of the teams were able to navigate to, or were able to receive the alert from the harmed team member in less than 1 minute, which was really good. Less than 1 minute from when he generated the alert, which was very, very good. And of course, the soldiers, they really liked the views, and they said they had no problem finding their hurt team member. The only thing they were concerned about is all of the phones didn't receive the alerts at the same time. So we set up the exercise that, whenever the team as a whole received the alert, they would need to go rescue their teammate. So what would happen is one person in the group might receive the alert before the rest, and then that person was tasked with going to find the teammate and then bringing him back, and then they would proceed with their mission. Other than that, they liked the color coding system, and they did not like having any text on the screen. They just wanted to see colors. So overall, pretty good. Okay, so on that same line, my lab mate is exploring having that same information available, but instead of using a color display or augmented reality, he wants to be able to have that information transmitted just using haptic feedback. So we actually built a vest that had the vibrating actuators in it, and then using the Arduino Lily pad to communicate with the phone, and then kind of do the same thing that the phones were doing, that the phones were doing, but instead it would deliver the information via the vest. So whenever a teammate was in danger, it would kind of give a quick, intense vibration to let you know, okay, an event has occurred. And then when the soldier would select that beacon signal, being the soldier's signal on his phone, it would then tap him in the direction that his teammate was located. So this could be potentially worn under a soldier's vest, and it would be able to give him like constant feedback on how his teammates were doing if he needed to have their attention. Okay. And that just kind of shows how the information was communicated. Okay, so I'll talk really quickly about some of the emotion classification work that we did. It kind of branched off of us wanting to provide a more intense level of team awareness. Rather than having specific alerts, we wanted to be able to also alert team members when they were experiencing signs of, PTSD, post-traumatic stress disorder, and also kind of keep a constant awareness of team members when they were, in feeling states of panic, for instance, and have that connection at all times rather than just whenever there was a crisis. So, of course, this is a pretty unique problem because in order to do that, the emotional classification and the feedback has to occur in real time, which was a pretty significant problem. So at that time, existing research didn't focus on real-time classification, and most of it was done offline after the data had been collected, pre-recorded. So the closest example that we had was a study conducted by Kim that identified emotional states with 5 seconds of signal data, and he was able to get 61% accurate on 4 emotions. So we conducted some preliminary research using video clips as stimuli and using EEG headset other than the one that we were currently using for the soldier interaction. But we tried to collect the data and see if we could, find any type of discerning clusters of groups that would identify, okay, this person is feeling angry or this person is feeling sad. And then we moved from using video clips to using the International Effective Picture System as stimuli. And then we started collecting data from the headset, but also from physiological sensors. We used a biosensor pack that was different than the mobile pack that we had initially used. And it was supposed to be more sophisticated, but the data turned out to have a lot of noise. So it was a really hard problem. But even still, through this entire effort, we came up with our own set of 14 signals. We had 20 signals of raw data, and then we came up with 14 features per signal, so 280 features total. And during this effort, during the first trial, we got a 43% accuracy on 6 emotions, which was a little bit higher than a previous research that we were basing it off of. But one significant thing we found that, I mentioned before that I come from the sketch recognition lab, so of course one of our main focus is sketch recognition, but applying features that we used to do sketch recognition actually applied very, very well to doing physiological signal classification as well. So we're kind of using or pursuing that avenue to see if like any other sketch recognition features also apply well to physiological signal recognition, mainly because the main reason that they did apply well is the fact that when you're trying to classify different types of sketch and different types of strokes, usually you're looking for changes in speed and significant changes in direction, which when also you're looking at physiological signals, that's also a significant identifier as well. So that's why they kind of cross-correlate really well. But it was unexpected, but it makes sense. Okay, enough of that. All right, so at this point we had pretty much implemented functionality that would allow soldiers to be able to have constant awareness of their teammates, and then also we started exploring ways for them to communicate, communicate whether or not their teammates were in danger, and then also trying to extend that to communicate physiological states that could help team members kind of keep an overall awareness of each other during a mission. That was our focus of that effort. Okay, last part. Run through this real quick. So moving forward, we knew that going into this effort that the teams that we were dealing with, specifically paratroopers, would not always consist of only human soldiers. So like after the soldiers have rendezvoused, assembled, and they're on the ground, later during the mission, they might require supplies or medevac. And currently the military is looking at using unmanned drones to be able to complete these requests. So we had started looking at ways to allow soldiers to be able to interact with drones that was easier than the current user interfaces that are being used. The one that's shown here is menu-based, and it requires a lot of experience and training to use. I mean, if you don't know what option you're looking for, and you're pretty much lost. Nobody can sit down and just use it straight off. So what we wanted to do was be able to use sketch recognition to kind of make the interface a lot easier and clearer for anybody to use. So we interviewed both Army personnel and Navy personnel for this effort, and kind of based our interface off of a current paper air support request form that's being filled out now. To kind of capitalize on the information that they're already familiar with. And we used a sketch-based application that recognizes mission planning signals, mission planning symbols to create kind of a mission narrative. So we merged that with an interactive map so that a person could basically just draw on a map and have a mission narrative be delivered to either a human pilot controlling a UAV or a totally autonomous UAV. Okay. So, the UI that we developed contains multiple layers. So it contains like I mentioned before, an interactive map layer. But then, as you sketch on the map, each one of the sketches becomes an interactive icon that you can then assign properties to. So instead of entering in the location and dimensions of a landing zone, a soldier just has to draw a circle on a map, and that will identify the landing zone, and then he can click on that circle and assign, properties such as weather, terrain, and other things that would be needed for a human soldier controlling a UAV to complete the mission. And then he can also use standard symbols for identifying location of friendly forces, which are circles, and then enemy forces, which are diamonds, and neutral, which are the green squares. Okay, so we conducted a preliminary evaluation of our interface, and it was received very well. We compared it to a radio scenario and found that the time to complete an air support request using our interface and using the radio scenario was pretty comparable. There was only about a 3-minute difference between each of those, but the benefit of our scenario is that the people on both ends didn't have to ask each other to constantly repeat instructions. Okay, so that's kind of the area that we had taken to pursuing human drone interaction in the same interface. And I think that's about it. So ongoing research for this area after I am gone, thank God. Ongoing research. So the people that I worked with, and then also some of the students coming in, are using kind of the interaction principles that we developed by doing this work, and are hoping to apply that to working with firefighters and rescue aid workers, and basically any team that needs to work in high stress environments where visibility is limited and communication is limited. One of our current students is also exploring using the types of interaction methods that we've been creating to work with people that work in high stress and office environments as well, and then using gesture recognition instead of gesture recognition instead of direct forms of communication to allow coworkers to kind of know when is a good time to disturb a coworker and things like that. And then, like I mentioned before, my lab mate is also pursuing the development of effective classification for use with delivering that type of information between teammates using effective haptics. So one teammate wearing a vest and then another teammate wearing sensors that will kind of monitor his overall state and then translate that information to a pattern of haptic pulses that his teammate could feel and then interpret. Okay, and then as I mentioned before, we already started conducting this research with to see if it's applicable for firefighters. But of course, they have much less visibility and a lot shorter time limit. Their stress is arguably a little bit higher, and then of course there's the environment creates a hazard for equipment. So those are just some of the challenges that we have to kind of look into when targeting this group. Okay, so in conclusion, we had developed a location-aware system to replace the sign rate for paratroopers. We had provided a hands-free solution that would increase situational awareness. We looked at delivering teammate status information between team members and in order to increase team coordination, and also presenting that information as subliminal feedback using haptics. And we also explored creating interfaces to allow team members to interact with their non-human team members as well. And yeah, that's pretty much it. Are there any questions?
Be able to take one or two quick questions.
Yeah, got a minute. Cool. Yes.
The hands-free solution.
Mm-hmm.
And
I can't hear. What?
Would there be a possibility to integrate night vision goggles?
Yeah. So the night vision goggles that they're currently using are kind of attached to their helmets. They're really, really expensive, but they have their own like little kind of, what do you call it, like display screen on the inside, so they can get information. We couldn't get one to play with. Like the manufacturer didn't want to give us one. We want to be able to kind of work with the equipment. The whole goal of this was to work with the equipment they were already carrying. Like the soldiers already had Android phones and they were already using those ruggedized computers. So we don't want to add stuff to them, but yeah, that's our goal. As soon as we can get our hands on one of those, yeah, that's the target. What?
Right, otherwise we'll give Danielle another big hand. And should we probably talk more about it?
Yeah.
Maybe.
Yeah, maybe.